Good morning everyone. My name is Monisha M and I am from Department of Software Engineering, Jain University. Today I am here to present our project titled Smart Traffic Light Controller with Pedestrian Crossing and Emergency Mode using STM32. Although my academic background is in software engineering, during my internship I got the opportunity to work on embedded systems. This project helped me understand how software and hardware together to solve real-world problems. I learned how to program the STM32 microcontroller, interface different sensors, and design a real-time traffic controller system. Now let me explain our project in detail. Abstract. The objective of this project is make traffic management smarter and safer. Instead of using traditionally fixed time traffic lights, our system can respond to real-world situations like pedestrian crossings, emergency vehicles, and changes in ambient light. The STM32 microcontroller continuously monitors different inputs and changes the traffic mix signals accordingly. The system also controls a servo barrier and sends live status updates through UART to a monitoring dashboard. Overall, this project demonstrates how embedded systems can improve traffic safety and efficiency. Problem statement. Conventional traffic lights work using fixed timings. They cannot detect pedestrians waiting to cross, cannot prioritize emergency vehicles, and cannot adapt to changing environmental conditions like day and night. These limitations increase traffic congestion and delay emergency services. Our goal was to design a smart traffic controller that overcomes these problems by making intelligent decisions based on sensor inputs and user requests. Objectives. The main objectives of our project are to implement automatic traffic light sequencing, to provide safe pedestrian crossings, to prioritize emergency vehicles, to automatically switch to night mode using an LDR sensor, to control a traffic barrier using a servo motor, to monitor the complete system using UART communication. These objectives together create an intelligent and adaptive traffic management system. System architecture. Now let's look at the architecture of our project. The system has three main sections. First is the input section. Here we have the pedestrian button, emergency button, and LDR sensor. During this project, I learned how to interface these devices with the STM32 microcontroller. The second section is the processing unit. The STM32 F103C8 microcontroller acts as the brain of the system. It receives all the inputs, processes them using software logic, and decides which traffic signal should be activated. The third section is the output section. This includes the traffic LEDs, pedestrian signal, emergency indicator, servo motor barrier, UART terminal, and the monitoring dashboard. Everything works together to provide adaptive traffic control. Hardware and software. The hardware components used are STM32 F103C8 Blue Pill, traffic LEDs, push buttons, LDR sensor, servo motor, USB to UART module. For software development, we used STM32QLDE, Embedded C, STM32 HAL Libraries, Lotus, Python Serial Monitor, HTMCL, CSS, JavaScript. Although I come from a software engineering background, this internship gave me practical exposure to embedded programming and hardware interface. System operation. Our system operates in four different modes. Normal mode. The traffic signal follows a fixed sequence. Green remains on for 10 seconds. Yellow remains on for 3 seconds. Red remains on for 8 seconds. Pedestrian mode. Whenever a pedestrian presses the crossing button, the STM32 receives an interrupt. Instead of stopping traffic immediately, it safely completes the current cycle before allowing pedestrians to cross. Emergency mode. When an emergency vehicle request is received, the controller immediately changes the traffic signal to red, opens the barrier, and gives priority to the emergency vehicle. After a few seconds, the normal traffic sequence resumes. Night mode. The LDR continuously measures ambient light. If the environment becomes dark, the system automatically changes to flashing yellow mode. When daylight returns, it resumes normal operation. Peripherals and roles. This project helped me learn several important STM32 peripherals during my internship. GPIO. GPIO stands for General Purpose Input Output. I learned how to configure GPIO pins to control traffic LEDs and read button inputs. It was my experience in directly controlling hardware using software. EXTI. EXTI stands for External Interrupt. Instead of continuously checking the buttons, the STM32 immediately responds whenever the pedestrian or emergency button is pressed. This made the system much faster and more efficient. Learning interrupts helped me understand real-time event handling. ADC. The LDR sensor produces an analog voltage. The STM32 cannot process analog signals directly. Using the ADC peripheral, I learned how to convert analog sensor values into digital values. These readings are then used to detect day and night conditions. PWM. PWM stands for Pulse Width Modulation. I learned how PWM controls the servo motor. By changing the duty cycle, we can rotate the servo motor and open or close the traffic barrier. UART. UART is used for serial communication. Using UART, our STM32 continuously sends system information such as countdown values, traffic states, sensor readings, and emergency events to the computer. These values are displayed on both the serial monitor and our web dashboard. Final state mission. The most interesting concept I learned was the find state mission. Each operating mode, normal, pedestrian, emergency, and night, is treated as a separate state. The controller moves between these states depending on timers, interrupts, and sensor values. Using FSM made our program organized, easier to debug, and very reliable. This internship gave me practical experience in embedded C programming, STM32 HAL libraries, debugging, and real-time embedded system development. Result and advantages. Our project successfully achieved all the planned objectives. The traffic signals change automatically. pedestrian requests are handled safely, emergency vehicles receive immediate priority, night mode operates automatically, the servo barrier works correctly, UART telemetry continuously updates the dashboard with live system information. Overall, the project demonstrates a reliable and intelligent traffic management system. Conclusion and future scope. To conclude this project helped me understand how software engineering concepts can be applied in embedded systems. During my internship, I gained hands-on experience with GPIO, EXTI, ADC, PWM, UART, timers and finite state machines. I also learned how software interacts directly with hardware to build real-time applications. This project improved my programming, debugging, and problem-solving skills while giving me confidence to work on embedded and LOD-based systems. In the future, we plan to integrate artificial intelligence for traffic density analysis, computer vision for vehicle counting, GPS-based ambulance detection, LOT clouding monitoring, smart city traffic coordination. These features will make the traffic controller even more intelligent and suitable for real-world deployment. Now here I will show a demo of our project. Here is our demonstration video of project.